Good morning, everybody. It's a great pleasure and honor for me to be here. Thank you very much for the invitation to this nice city in this nice hall. I'm going to talk about the buried giant. The buried giant, which is construction materials, shape the environmental footprint of buildings. I have a dream, and I guess you share this dream. Imagine you are hiking in the mountains, and towards the evening you reach the mountain lodge. You enjoy a good lunch, a good dinner. It's time to go to sleep. You move upstairs to the sleeping rooms, you open the door, and then your wish comes back to you. 0 emissions. 0 emissions, that's what we are heading for, especially when it comes to carbon emissions, net zero emissions we want to reach. I will touch on 4 questions in the coming 20 to 25 minutes. The first question is, on whose shoulders do we stand? Where do we come from? The second one, are construction materials really the buried giant or not? The third one, net zero emission buildings, are these castles in the air, or can we really make them get into reality? And finally, what remains to be done after all? We faced exponential growth today. We faced it in the past. You see on the right-hand side a chart on the coal consumption in England in the 18th century. And there was Professor William Jevons, an economist born in Liverpool, UK. He looked at these numbers, at these curves, and he thought, well, what needs to be done? What can we do with this exponential growth? We cannot eternally grow in a way because we run out of coal. So he had thought about, well, we have to make the momentous choice between brief greatness and longer continued mediocrity. He advocated for greatness. Make Britain great again. That was his advocation. There was another person, again a man at that time. He thought about a more sustainable solution, the use of renewable energies. And he was saying people will then have to rely on the energy, which means after we have run out of coal, we'll then rely on the energy which the sun will continue to supply us with rays in the course of the distant future. Sustainable use of energy using the energy of the sun. And this was Rudolf Clausius, born in Poland. He was professor at ETH Zurich, an earnest person, as you can see. But then we come to Professor Patrick Geddes. He was professor here in Edinburgh, born in Scotland, and somewhere down there, there's the Patrick Geddes Hall, so for students to live there. And he, to my knowledge, he was the first person who made a life cycle consideration without knowing the word life cycle assessment, though. And this is his graph. It's about coal and its use. And on the right-hand side, you see the sources. It's qualitative, but that's the coal available in the mine. Then you exploit it, you manufacture it and transport it. You lose a certain amount of coal, and you need a certain amount, invest a certain amount of coal to produce the energy, to extract the coal, to manufacture it, to transport it, to exchange it. And this is the ultimate product, so the coal that you then fire in a steam engine. In a steam engine, you know that the efficiency may be 25, 30% at that time. And that's the final energy you get out of the coal. So 10% of the coal you extracted is finally used in form of usable energy. Coal was very cheap at that time. He was an economist and biologist, and he said, well, it cannot be that coal is that cheap and that poorly used. So that's why he said we need another measure to show how poorly we use the coal. This is the part that we are using. 1 century later, Boustead and Hancock, again UK people, they issued the Handbook of Industrial Energy Analysis, which is one of the compilation of cumulative energy demand figures for lots of materials, different sources. They indicated where they collected the data from, they compared it to the different sources, and so on. Well, that was in 1979. Later on in the 80s, we see here one of the first zero operational energy buildings erected in Switzerland. And at the ETH, they made a life cycle assessment on those buildings and the measures to reach zero energy during operation, to check whether the investments were worth the savings for the operational energy. There were comparative assessments of insulation materials drawn by hand by architects. They made these process trees to show how complex or how simple the supply chains of these insulation materials were. This document was quite popular in our country. We sold them thousands of copies to architects and designers. Then in the 90s, a group at ETH compiled life cycle assessment data on the energy supply. Ökoinventare von Energiesystemen. This was one of the first ecosystems of data on energy supply, material production, transports, and end-of-life waste management services. And it was awarded by an industrial award in the mid-90s. And then in the 90s, we had the Econent database that was published the first time 20 years ago, which is let's say, a growing set of data on different economic sectors that makes life easier for architects and planners to assess buildings and building variants. Another curve which shows an exponential growth. We see here the global CO2 emissions from 1850 to 2010, and I just want to place these different events or these different publications on this timeline. So Patrick Geddes was here. You hardly see any exponentiality at this time when looking at the bigger scale. Later on, Boustead and Hancock, when they published, obviously there was some decrease in the emissions following that, possibly. When these zero operational energy buildings were constructed and the first life cycle assessment databases were out, we see a certain shift in or decline in the increase of the emissions. But when Econent was published, there was a steep increase started. So the question is, how can life cycle assessment data really help to reduce the emissions rather than to boost them? Obviously, it's not yet come into effect. If we now turn to the construction sector, there was a meta-assessment of life cycle assessment of buildings that assessed hundreds of published papers on the greenhouse gas emissions of construction and operation of buildings, both residential buildings and office buildings. If you look at the residential buildings, we see on the left bar existing standards, buildings according to existing standards, or rather elderly buildings, the new standards that are, let's say, the state of art of today, and then new advanced standards which are at the forefront of development. What we can see is that the operational part, the blue part, is steadily decreasing. So with new regulation, with new standards, the operational impacts decrease substantially. But on the other hand, the embodied emissions, they tend to increase. So we face the issue that construction measures are taken to reduce operational energy demand. So what we need is consider both, not just operational emissions, operational energy demand and emissions, but also the embodied emissions, the embodied energy needs to be taken into account. I tell you some insight, or give you some insight into the history of how the construction sector in my country, in Switzerland, is using life cycle assessment for assessing their buildings. We have this KBOB recommendation, which is now called 2009/1. It was first published in 2007, and it contains data on construction materials, building technology, energy supply, transport services, and waste management services. You may recall the first database issued from ETH contained energy supply, building materials, transport services, waste management. These are the 4 sectors that at least need to be covered when to assess the life cycle of buildings. What are the system boundaries of those data? We on one hand have the materials production, starting with raw material extraction or the recycling, material recycling and the building material production. And at the end of life, the disposal, either incineration or landfill. It might be recycled or reused. This is outside the system boundary. There are no credits in this database. And also construction, the use in buildings is not part of this compilation of data because these materials may be used in different contexts, and the use phase is then introduced by the architects, the designers, when they design the building. What environmental indicators do we have? We do have the greenhouse gas emissions, the blue part, for production and end of life. In red, this is the, let's say, Bousted and Hancock kind of view, cumulative energy demand, separated in renewables and non-renewables. And we have in Switzerland the total environmental impacts according to the ecological scarcity method. So a single score indicator that tells you how impacting is construction material or an energy supply on the environment in total. And finally, newly introduced the biogenic carbon content expressed in kilogram carbon, not in kilogram carbon dioxide. And there are further features, no benefits and loads beyond the system boundary. There's unique identifier numbers, and there are company-specific data available. So if a company wants to be part of this table, they can perform life cycle assessment, let it verify, and get into the table. Now we have a 25 years record of these data, starting with the ETH database in '96 and ending with KBOB 2022, so the last year's issue of those. I've made timelines for 5 different materials: concrete, steel, aluminum, glass, and wood. They are normalized by 100%, and please do not compare the numbers per kilogram of the different materials. This is just to show how the emissions evolve. We have 2 products, 2 materials that drastically reduce the emissions. This is structural steel and wood. So we have, there's a factor of 3 with wood, factor of 2.5 with steel. Aluminium could halven the emissions, 50% reduction over the 25 years. With concrete, it's a reduction of 30%. That's rather small. And with glass, I don't know, they have slept 25 years. Nothing happened. It even seems to be increasing a bit. Now, we made an assessment on how could materials production look like in 2050, looking at the blueprints and interviewing associations of concrete, of steel, of aluminium, what they see would be a construction a production way, a way of production that is Paris compatible, Paris goal compatible. And these are the blue figures. We see that all of the materials, or most of the materials, may drastically reduce the emissions down to maybe 1/4 of the initial ones, except for wood, which has already rather low emissions, or has decreased the emissions drastically before, and has not that much to reduce. But still, the bars are positive, which means we still release greenhouse gas emissions, and what we would need is get to net zero in the end. We assessed 2 buildings using these future data. One is an office building, which has a concrete kernel and wood facade, a heating and hot water demand of maybe 25, 23 kilowatt hours per square meter in the year, ventilation and lighting demand of electricity of 20 kilowatt hours, and a residential building, which is a massive construction with slightly higher heating demand, but a lower ventilation and lighting demand. Now, if you look at the greenhouse gas emissions of the office building, the lower part is how the performance is today. The light red part is the operational part, and all the rest is for the embodied emissions. A large part is building technology, like the electrical wiring and so on. And the other parts are rather evenly spread. Now, if we look into the future, one could about halven the emissions with these, let's say, with these. Is this operational energy? Oh, the building is said to last for 60 years, and the numbers are per square meter and year, for a lifetime, or let's say an assessment time of 60 years. Now, we have a standard in Switzerland that tells you if you are Paris goal compliant or not. And for the embodied part, you need to reach 9 kilograms. For the embodied and operational part, you are at about 12 kilograms CO2. So this building already today meets the limits easily, and in the future even more. The residential building is at about 12 kilograms CO2, so it just reaches the reaches the limit, and the embodied part with a slight overshoot of the embodied part as of today, but in future with a reduction of 55 to 60%, it's also below the limits. But again, we see quite a lot of emissions still today. We need to go to net zero, and the question is, how can we do that? And how does net zero works? We see here the Hortus building of Herzog and de Meuron, close to Basel. They have the ambition, together with the commissioner, to build a building that pays back the grey building energy within 30 years and gets energy positive 30 years, after 30 years. So that's their ambitious goal that they want to reach. And the question is, can they reach that? But we need to think about what is a net zero emission building at all. We see here in yellow the life cycle of the building with the product stage, the construction stage, the use stage, the end of life stage. In blue, we have the operation stage with the energy consumption during operation, water use, and so on. And the red part is the potential benefits and loads beyond the system boundary. Now, net zero greenhouse gas emission buildings, we can limit that to the operational energy of the regulated energy part only. That's a narrow definition, but some people use this system boundary to get net zero buildings. We can enlarge the operational energy to unregulated building energy consumption and to the user and use-related energy. Or we can go even further and include the embodied part as well. And this is what what I advocate for, to use the full life cycle to check whether or not a building is net zero or not. If we talk about net zero, we need a compensation of positive emissions with withdrawals, and they're with offsets. And the Oxford principles, they classify the different means of how to offset emissions. And the first one, the red one, is potentially avoided emission. Producing electricity on the building with photovoltaics, feeding it into the grid, and let's say we save coal power electricity being produced elsewhere. And then we take those saved emissions into our accounts as negative emissions. The second one would be emission reductions, so like laughing gas emission abatements, methane abatements, and so on. We may have emission reduction where carbon is stored with changes to agricultural practices, so we store more carbon in the soil. Again, emission reductions using carbon capture and storage on industrial facilities and fossil fuel power plants, so we reduce the amount of fossil carbon that is emitted to the air. And in the blue part, it's carbon removal. So we really store carbon with afforestation, reforestation, but it's on the short term. And the carbon removal on the long term will then be if we directly extract carbon from the air and store it on the ground, or when we burn bioenergy and capture and storage this one. There are different ways of how we can account buildings as net zero. We can do that with the potentially avoided emissions. We can do it with economic compensation, buying CO2 emission certificates. These are in the red part, so they are more or less shifting emission reductions from one sector into the building sector. And we can have technical removals where we invest in removal technologies like Climeworks and others, where CO2 is removed from the atmosphere and stored on the ground. Or we may, most ambitiously, use materials that simply don't emit CO2 in the supply chain. Not yet existing, but this is the way we might head to. Some examples of CO2 removals. This is a concrete made from biogenic CO2 that was extracted from biogas purification to recarbonize recycled materials, recycled concrete aggregate. So we have about 10 kilograms of CO2 removed per cubic meter of concrete. Remember, producing 1 cubic meter of concrete emits 100 to 200 kilograms. So it's a 5 to 10% reduction or contribution in reduction of emissions. Bio-based materials might be another solution if stored permanently. We see here the temporal nature-based carbon removal. What we can see, or what the chart tells us, if we additionally remove carbon in large amounts, so 300 gigatons of CO2, if we remove that temporarily and release it 30 to 50 years afterwards, what will happen on the global temperature and the CO2 concentration? We will see that the concentration will drop for a certain time, but then again it will reach the concentration, as it were, without temporary storage and release. So we are at 2,100, we are at the same concentration, we are at about the same temperature increase. This is the 1.5 degree increase we want to head to. So in the most ambitious scenarios, climate emission scenarios, we may have a slightly lower peak temperature, but in the end, the overall temperature increase will be at the same time if we release the CO2 that we captured later on. And this is when it comes to wooden materials, whether we can use them for reaching net zero buildings. It can be considered, to my view, as a negative emission technology if it's multiply used, so after the end of life of one building it's used again in the next one, or if permanent sequestration for at least 3,000 to 8,000 years is guaranteed. And how can you ensure that? There are different ways to do that. You may have legally binding entry in the land register. You have that today. If you buried an oil tank in your garden, you had a note in the land register to remove it once it's out of use. So this would be one solution. Another solution would be on a national level to introduce carbon capture and storage in waste incineration plants, waste wood power plants, and so on, to be sure that most of the biogenic carbon is not released again. So my conclusions: buildings and the supply chains are important emitters of CO2 and greenhouse gases. Embodied emissions are more and more important, despite significant reductions in construction materials production. So there's a lot of further efforts needed to reduce, in the material industry needed to reduce the emissions there. And negative emissions are indispensable to reach net zero emission buildings and societies. What remains to be done? In one of the International Energy Agency's annexes, the Monte Verita Declaration has been published, and one of my favorite recommendation to policy is introduce legally binding target values for carbon footprints of buildings until 2025, 2 years from now, with a reduction path to net zero by 2035, 12 years from now, to have buildings that have to be net zero on their life cycle. This has been signed by more than 40 scientists from 25 countries worldwide in this annex. This is it. Thank you very much, and I look forward to your questions.